Hello, this is Dr. Roty, and in this video, I'm going to go over the practice exercises for Test 2. So the first question says the weekly salaries of teachers in one state are normally distributed with a mean of 490 and a standard deviation of 45. And it asks what is the probability a randomly selected teacher earns more than $525 a week. So I'm emphasizing a randomly selected teacher. That's one teacher. So I have X representing the salary. That's normally distributed with a mean of 490 and a standard deviation of 45. And the question asks if one single randomly selected teacher earns more than $525 a week. So a single teacher, that's a single value of the random variable X. So its probability of X is greater than 525. So if you can draw a sketch for yourself. I'm not too skilled at drawing, so I use this computer printed bell curve. But you can sketch out a little sketch for yourself to help you see what you're doing. Just kind of just a guide, so when you go to type it in the calculator, you have a visual. And you're looking at, is it greater than 525? So somewhere around here is 525, give or take. And you want greater than. So you want this area under the curve to the right. And that is calculated using the normal CDF function in the calculator. CDF. So I come here to the calculator above vars. It says DISTR. So that stands for distribution. So I'm going to say second. I'm going to hit the vars button for distribution menu. I want number 2, normal CDF. So then I have what's my lower bound, my upper bound, mean, and standard deviation. So the lower bound is the 525, and the upper bound is infinity. So I put in 525. The calculator does not have an infinity button, but you just put a really giant number. I like to use 10 to the 99, or I can type a bunch of 9s, but this is a huge number, 10 to the 99th power. For all practical purposes, that's infinite. Then I put in the mean, which is 490. And then I enter the standard deviation, which is 45. And then I hit enter on paste. It'll put the command in the command screen. And then I hit enter. So this probability is 0.2183. Again, on the test, read how many decimals they want you to round to. I'll round to 4 in this case, but just whatever the problem tells you, round to that many decimals. But in this problem, you get 0.2183 is the probability, and I'm going to look carefully. It says probability, so I don't have to convert that to a percent. I leave it written as a decimal form. Number 2 here, it says a bank's loan officer rates applicants for credit. The ratings are normally distributed with a mean of 200 and a standard deviation of 50. So this is a shorthand to record that. If an applicant is randomly selected, what percentage of ratings are between 200 and 275? Now, it's asking for a percentage, and it's an applicant, so it's just X. So I have a single observation, and I want to know what's the probability that in the stated distribution here that it's between 200 and 275. Because the normal is a continuous distribution, I don't have to worry about that because either way it's equivalent in a continuous distribution when you do the calculation. So in the middle here I have 200 and it wants to know what's the probability of being between 200 and 275. So I want this shaded area here under the curve, and again I'm going to use the normal CDF function. Second distribution, normal CDF. Now my lower bound this time is 200. My upper bound is 275. My mean this time is 200. And my standard deviation is 50. And then I paste and hit enter. So that probability is 0.433. If I round to 4 decimals, 0.4332. So if I change that to a percent, because it asked what percentage, I would get 43.32%. Again, pay attention to the rounding rules that are given on your test. Number 3, it says a physical fitness association is including the mile run in its high school fitness test. The time for this event is known to possess a normal distribution with a mean of 450 seconds and a standard deviation of 40. So this is normally distributed with a mean of 450 and a standard deviation of 40. The Fitness Association wants to recognize students whose times are in the top or fastest 10% with certificates of recognition. What time would a student need to beat in order to earn a certificate of recognition from the Fitness Association? Well, you could sketch it out to help you visualize what you want. What I want is some value here, okay? Some value of X that will separate the top 10% of times, so I'll write that as a proportion, from the lower 90% of times. Okay? So I already know the probability here. So I'm not going to use normal CDF because I'm not interested in the probability. I already know. The probability that I'm greater than X will be 0.10 or less than X would be 0.90. What I'm interested in is the value of X. So I'm doing the backwards of normal probability. I'm doing inverse norm. Now in the TI84, the inverse norm finds the percentile. So in this case, I would have to convert if I have a regular TI84, not the CE version. In my mind, I have to say, okay, well, if I have 10% above this value, the amount below is 90% or 0.9. And so the inverse norm does percentile in the TI84, but in the CE, you can actually indicate if you're looking at right tail, left tail, or the middle. So let me show you this. I'm first going to do this as if it was a regular 84. So second distribution, and I go to inverse norm, which is the third choice. So I'm going to immediately go down for a minute here. Well, it won't let me. So first I need to put the area. So what I'm going to do is first, as an 84, you want to look at what is the percentile, the 90th percentile to the left. What is the mean? 450. The standard deviation is 40. And then I'm going to hit enter on left. So on a TI84, you won't have this tail here. It's defaulted to left, but you don't have a choice. So if you have a TI84, you need to do inverse norm and look at the percentile, the area below, which in this case is 0.9. And so this is what I get. Now, let's say you do have the TI84 plus CE. I go into second distribution. I still choose inverse norm, but notice I have 10% shaded to the right. So you could come in here and simply do 0.1 and choose the right tail. And then if I hit paste, so 10% to the right is equivalent to 90% to the left, right? That makes sense. And sure enough, you get the same answer. So if we round that to 1 decimal, I get the time is 501, or 2 decimals. Or yeah, 1 decimal. 501.3 seconds would be the minimum time to be in the top 10%. So again, if you have a TI84, not CE, if you don't see the choice of what tail to use, it's going to default to left, and you have to first convert these inverse norm problems always to a percentile. If you have a TI84 CE, you can choose what tail you want to use. Just make sure that when you do that, you have the appropriate percentage entered. Number 4, it says the weights of the fish in a certain lake are normally distributed with a mean of 19 pounds and a standard deviation of 9. So X is normal with a mean of 19 and a standard deviation of 9. If one fish is randomly selected, what is the probability it will be between 16.6 and 22.6 pounds? Now, what I'm going to do, actually, I'm going to copy in number 5 as well, because I want you to see the difference between the two questions. So if I look at number 5, it reads almost the same. It's the same context. It wants even the same range of probabilities between 16.6 and 22.6. But notice in number 5, it says if 9 fish are randomly selected, what's the probability, the mean or average weight? So if you look at 4 and look at 5, they're very similar, but in number 5, you're talking about the probability of an average or a mean of a selected amount, whereas in number 4, it's just 1 fish. So for number 4, first let's make a little sketch. It turns out the sketch is going to look the same, really, because we're not actually putting the exact bell curve. This is just a standard bell curve, but just so we can get an idea of what we're doing. And somewhere down here, you know, is 16.6, and somewhere up here is 22.6, give or take, you know. And so we want the area between these two values. Well, in this case, the mean is 19, standard deviation is 9. So I'm going to use my normal CDF, and I'm going to say my lower bound is 16.6, and my upper bound is 22.6. My mean is 19, and my standard deviation is 9. And then paste it. So I get 0.2606. So the probability here, probability that X is between 16.6 and 22.6 is 0.2606. Now, in number 5, note since it asks for the probability of a mean weight being between these values, I'm no longer talking about just the random variable X. I'm talking about the sample mean of the random variable X bar. So what I have to do then is say, well, what's my distribution of x bar? Well, since x is normally distributed, so will the sample mean, right? No matter what the sample size, if your original population is normal, then your x bar, your mean will be normal, your sample mean. If you have a skewed distribution, but you have a large sample, then you don't worry whether the original distribution is normal. In any event, x bar is going to be normal with the mean of x, which is, so it's still 19. So the average of x bar is equal to the mean of the population. Then remember that sigma x bar, the standard deviation of x bar, is the standard deviation of the population, x, over the square root of n, your sample size. Well, that would be the standard deviation of the population is 9 right here. Well, it's given right here too, right? It's the same distribution, but here we're looking at a mean, there a single value, over the square root of the sample size, which also happens to be 9. That's coincidental. Well, square root of 9 is 3. So 9 over square root of 9 happens to be 3. Now, you don't always get a nice number like 9. That's a perfect square. So use your calculator and calculate this out, right? You can do 9. I'll just show you the steps, even though the math is easy on this one. You might get a standard deviation of 27.3 or something. You're not going to take that square root in your head. So you do like that. Just 9 divide by, there's the square root symbol in this kind of calculator. You get 3. All right. So if I do second distribution, let me put the 3 there. Now I'm looking at this distribution. I do normal CDF, but now I'm going to change that sigma to 3. So the mean is still 19. My boundaries, read the problems carefully when you're doing your test, but in this case, the boundaries are the same. The mean is 19, the standard deviation is 3. So the standard deviation just got a lot smaller, right? It was 9, now it's 3. So that bell curve is going to squeeze in and be taller. And what's going to happen is you're going to have a lot higher probability of being between those values now, because the tails get smaller. So these tails will get smaller, which means there's more area in the middle. And so it won't be surprising to see our probability get higher. When I say the tails are smaller, I mean the vertical distance between the horizontal axis and where the these tails are above the axis. Because when you lower the standard deviation, the width here, this width gets smaller. And so you get smaller areas out in the tails. Okay, so the probability there then now became 0.6731. So on average, you're going to get a much higher probability between these limits than you do for a single observation. Because single observations just have more variability, there's going to be more individual observations out in the more extreme values than if you take averages. So remember, if you're asked to find the probability of a mean or an average, to first consider that you have to do the standard deviation and the mean of the sample mean, but the mean of the sample mean happens to be just the mean of x. But the standard deviation you must divide by the square root of the sample size first when you're finding probabilities of averages. Other than that, it ends up being the same kind of function, normal CDF in this case. Number 6. Smith is a weld inspector at a shipyard. He knows from keeping track of good and substandard welds that for the afternoon shift, 5% of all welds done will be substandard. If Smith randomly checks 200 welds completed that shift, what's the probability he will find more than 8% substandard welds? So we're looking at probability of a percentage. Probability that the proportion from a sample is greater than 0.08, right? So we're told that the population proportion is 0.05. We're told that n is 200. So I want to know the distribution of p hat. Well, the mean of p hat is p, which is 0.05, and the standard deviation is the square root of p times 1 minus p over n, which is the square root of 0.05, and then 1 minus 0.05 is 0.95, all over 200. And then you just compute that in the calculator. So 0.05 times 0.95 divide by 200, and I get my sigma p hat n is equal to 0.015411. I'll carry several decimals. I have 0.05 here in the middle, and I want to know what's the probability that he finds more than 0.08, right? So I'm going to use the normal CDF command. Second, distribution, normal CDF from 0.08 to infinity. My mean is 0.05, and my standard deviation 0.015411. I carry several decimals on here to avoid rounding errors, and then enter. And then, so this is our probability. So the probability, I'll just put it right here in the middle, so I wrote it there, will be 0.0258 if I round to 4 decimals. And again, pay attention to the number of decimals that the test asks you to round to. Number 7, the principal randomly selected 6 students to take an aptitude test. Their scores were as follows. Determine a 90% confidence interval for the mean score of all students. So my confidence level, C, is 0.9, right? I'm trying to estimate the mean score for all students. I want some confidence interval estimate for all students. So I have a small sample. I don't know the population standard deviation. So I'm going to use the t-interval command. T-interval. The t-distribution is an approximate z distribution. So I come into my calculator, and this will be under the test menu. Stat tests. And I go down to number 8, t-interval. So choose number 8, arrow down or hit 8. And notice that when I do this, I can put in a data list. Okay, so the data says right here is an L1, and I can go to my C level. Of course, I haven't entered the data yet, so I have to go do that. And I change that to 0.90. Now, I have 2 choices. I could say, hey, look in list 1, and it'll do it automatically, or I could run one-var stats and then run with stats. So let me show you what I mean. So I'm going to go to stat, edit, and in list 1, I'm going to enter those numbers. So now I have this data here typed into list 1. So I'm going to quit, and I'm going to run the one-var stats. You don't have to do this. It's up to you. But I'm going to run it so that it's done. So I run one-var stats and hit calculate, and it gives me x bar, s, and n, which are necessary to run that function, the t-interval. So let me go back to t-interval. Stat, test t interval. Arrow down to t interval, or hit the number 8. If I have a data set, I just tell it what list it's in. So be careful. Make sure frequency is left at 1. And then above the numbers, you can see how I can hit second and indicate the list. So if you have a different list there, the way to get list 1 is hit second 1 or second 2, whatever list you put the data in. And then I indicate my confidence level, and then I hit calculate. And that will give you your confidence interval. If you choose stats, well, you have to input X bar, S, and N, and then the C level always. But if you run one-var stats first, and make sure you don't just put it in the list, but you run one-var stats, it will save these in its memory and copy these values over. So whether I use stats for data here, since I ran one-var stats with the data, I'm going to get the same output. So for instance here, my interval then, and interval notation, and so you have different ways you show a confidence interval. A lot of times you just show it in this interval notation, where here you have the 79.586 to 86.88, or sometimes you list it this way, and let's round this to 2 decimals. So that would be 59. And 86.88. So that would be the interval listed in this format or interval notation. You can see it on here on the calculator. Now let me show you again. If I do stat tests and I pick number 8 t interval, and let's say I chose data, we're going to get the same result. I tell it where the data is. I tell it leave frequency at 1, 0.9 for the confidence level, and hit calculate, and notice you get the same output. Number 8, it says how many commuters must be randomly selected to estimate the mean driving time of Chicago commuters when we want a 90% confidence interval that the sample mean is within 4 minutes of the population mean, and the population standard deviation is known to be 12 minutes. So they're telling me that this is sigma. This is my confidence level C, right? And this is the number 4 here, the value 4, I should really say, is our margin of error, right? And so there's a formula that tells us for a given margin of error that N must be at least, okay, the critical value Z that would give us a 90% confidence interval times sigma divide by the margin of error squared. Now, a lot of times it's how many commuters must be to make sure it's within. Technically it's greater than or equal, but when we run this formula, we do it with just equal, and then we say, hey, it's got to be at least that. So if we get a decimal here, no matter what the decimal is, we always round to the next whole, right? It could be 79.0000001. You would round that up to 80. Because you can't take 0.0000001 of a person, and these are discrete units that you're selecting. And if you take 79, like, you would have a margin of error then that would be slightly bigger than the specified margin of error. So you want to make sure it's within 4 minutes, the margin of error. So you have to always round up. You can't just round by your normal rounding rules. But it's pretty easy. You drop the decimal and add 1 to the integer, because it's very rare you'd get an actual whole number here. Almost impossible. So Z star, what is that? So you see sigma here is 12, and E is 4, but what about that Z star? That's not given in the problem, but they gave you 90%. Well, this 90% confidence level can help us find what this critical value Z is. So remember, a Z is a standard normal with a mean of 0 and a standard deviation of 1. And I want 90% confidence. So what I want in the Z are these limits right? And Z star is really the, we're looking at the absolute value, so we don't care about the negative. So I'm going to use the positive value that I get from this process that I'm about to do. And I want this area between them to be 0.9. Okay? So I want this area between them to be 0.9. And I have a video that I presented on Canvas that gives a quick and easy way to trick the confidence interval command for a Z to give me these limits. Because if you have a standard normal, a mean of 0, and a standard deviation of 1, then the values here, right, if I run a confidence interval for Z with mean of 0 and standard deviation of 1, I'll get these values. So here's what I'll do. I'm going to come in here and say stat test, and I'm going to use Z interval, which I don't really use that with data, but I'll use it here. And I'm going to say I have stats. Then I'm going to say that my standard deviation is 1, and that my mean is 0, and that my sample size is 1. Okay? And then I pick my confidence level, whatever it says. So this time it happened to say 0.9, and that's already in there, but whatever confidence level, put it in as a decimal, and then hit calculate. And what that'll do, it shows Z interval, and because the confidence interval formula, the way I put x bar equal to 0, or mu equal to 0, x bar equals 0, excuse me, and n equal to 1, the way the confidence interval formula works, if you did it by hand, the algebra works out where you get just the Z star value. So my value here then is 1.6449, so I'm going to plug that in. And a lot of times we round Z's off, but I'm going to use that 1.6449 times my standard deviation is 12 all over the margin of error stated to be 4 and then squared. So again, this process I just did, if you look on the videos that I put during the weekly lessons, you'll find this tutorial also in the TI84 tutorial section on how to find the critical value using this method. So then I come in here and I'm going to literally type what I see here. Because of the nature of multiplication division, I can do this times 12 divide by 4 and then squared. So I get 24.35. And normally you would say, oh, if I round to a whole number, that would be 24, right? But when you do these sample size problems, always round to the next integer, next highest integer, which is n equals 25. Okay, also, if you have a CE calculator, there's another method to find the critical value. Second distribution, inverse norm. If I look here, I have 90% in the middle. So I can say 0.9, 0, and 1 for my mean and standard deviation and choose center. And that will also give me the limits. But if you have a regular TI84, it's easier to do the method I showed you using the Z interval command and putting in 0 and 1. So let me show you that again. Z interval is number 7. To find a critical value, put sigma as 1, x bar as 0, put n as 1, then just put in your confidence level, and it will calculate for you the limits that you need to find the critical value. Use the positive number. Alright, so this is how you do sample size. Minimum sample size for a given margin of error when you're finding a confidence interval of a mean. That's this formula. A survey of 865 voters in one state reveals that 408 approve an issue before the legislature. Construct the 95% confidence interval for the true proportion of all voters who favor the approval. So this is wants a confidence interval for a proportion. It gave me n, it gave me x. X the number of successes. Success is, in this case, defined as approval because right here, favor approval. So I want to run what's called the one prop z interval command. So under the stat menu, go to tests. So stat key, over to test, and you see one prop z test, but you don't see the interval. I need to keep going. Just arrow down, cursor down, one proportion z interval. It's the letter A. So I could do alpha A, but for me it's easier to go down. There we go. So x is 408. And then 865. Confidence level is 0.95. So 408, 865, 0.95. And then calculate. And so here's my interval. So this is the way it looks, interval notation. You may see that on the test, or it may have like P in the middle. Notice it's the parameter when you do it in this form. And let's round this to 3 decimals. So 0.438 is my lower limit here. Up to 0.505. So this would be it listed with the inequality, with the population parameter in the middle. And what you see on the calculator here is interval notation. You could be asked either way to type this answer in. State Highway Patrol official wishes to estimate the number of legally intoxicated drivers on a certain road. What size sample should be obtained in order to be 98% confident that the sample proportion will not differ from the true proportion by more than 5%. So again, I want a sample size given a margin of error and a confidence level. My margin of error in this case is 0.05. My confidence level is 0.98. Now, I need to find Z star because for part A, I need to use the following formula. N will be P, 1 minus P, Z over E squared. So the P is either given in the problem, or if you have no idea what P might be, okay, then you just assume P is 0.5. Well, if I do that, okay, so that's the general formula. But notice if in part A, it doesn't give me any idea what P might be. Now in part B, it says assume that it's 0.65. Well, if you have no prior estimate, then what you do is you assume that P is 0.5. So given no prior estimate, you assume that P is 0.5. Well, 1 minus 0.5 is 0.5, and 0.5 times 0.5, it turns out is 0.25. So if you go and look at the textbook, you will see that they will diminish it to this, saying that if you have no prior estimate. That's a Z star, by the way. But you could also just, use the one formula and say, hey, if I don't have a prior estimate, just use P equals 0.5. All right, so now we have to figure out, we know what E is. E is 0.05. We need Z star. So like before, I'm going to use this the z-interval to do this. I'm going to trick the z-interval into giving me the critical value. There's number 7. And I'm going to say that sigma is 1, x bar is 0, and n is 1, and I want 98%. Okay? So this is how I'm going to get my critical value z star. Use the z-interval, make sigma 1, x bar 0, and n 1. And that will give me the z value. It'll give me the middle 98% limits in the z normal, standard normal distribution. So my z star is 2.326. So 0.25 times 2.326, 2.326 over the margin of error is 0.05. So this is important. Enter your margin of error as a decimal. Right here, I did it here. So a lot of people forget, they put in 5. It's 0.05. All right, so 0.25 times 2.326 divide by 0.05, and this is squared. The calculator knows the order of operations, so it knows to do square on what's in the grouping here, and then multiply by 0.25. So look at here, I get 541.0276, so I'm going to round that up to 542. All right, now it says repeat part A, but assuming that previous studies found 0.65 to be the proportion. So we have a prior estimate for P here. So I'm going to use this formula with 0.65 as P. So 0.65 times 1 minus 0.65 times 2.326 over 0.05 quantity squared. So 1 minus 0.65 is 0.35. So I'm going to go in the calculator, I'm going to type 0.65 times 0.35. You could type 1 minus 0.65, but since that's an easy thing to figure out, I did that to save some keystrokes. 326 divide by 0.05 squared. So this is now this right here put into the calculator, and I get 492.335. Again, you might normally think, hey, I round to 492, but this is at least this many people you survey, okay? Or in this case, he wants, at least this many people in the sample. So you have to round that up to 493. So we'll survey at least 493. Number 11, it says a local retailer claims that the mean waiting time is less than 5 minutes. A random sample of 20 waiting times has a mean of 3.4 minutes. That's X bar, that's from the sample. And a standard deviation of 2.1 minutes, that's S. At the alpha of 0.01 level, the significance level of 0.01, test the retailer's claim. Assume the distribution is normally distributed. Round test statistic to the nearest thousandth, so 3 decimals. All right. What I want to do here is a t-test of a mean. I want to do a hypothesis test of a mean. I don't know the population standard deviation. I have the sample standard deviation. I'm going to use the t-test. So the first step, though, is to state my hypotheses. My null hypothesis and my alternative hypothesis, sometimes called test hypothesis. Well, hypotheses are always stated in terms of population parameters. And so the claim is that it's less than 5 minutes. So I'm going to say, hey, the waiting time is 5 minutes. And then the claim is, in this case, the alternative, mu is less than 5. So we want to see, is there evidence to support this claim? Well, I need the test statistic t, and it's going to have n minus 1 degrees of freedom, so in this case 19. Okay, and then I need my p-value, and then based on the p-value, we'll make our decision. Okay, so I'm going to say stat, test, and number 2, t-test. Now, we were given summary statistics. We weren't given data, so I'm not going to highlight data here. I'm going to use stats. Mu 0 is equal to 5. That's the null hypothesis mean. X bar is the mean from the sample, which is 3.4. S is the standard deviation from the sample, which is 2.1. If you were given a data list, you could put the data in the list, run one var stats, it would copy these numbers over, or you could highlight data and say, hey, it's there in L1 or L2, wherever you put it. N is 20. What is the form of my alternative? It's less than, so I have to make sure I hit enter to make it stick. It's less than. I'm going to ignore color here because I'm not going to draw it. I'm just going to calculate. Okay, and I hit calculate. So my test statistic is negative 3.407. So again, it said round to the thousandth, so that's 3 decimals. Pay attention to the rounding on the test. I say that a lot, but it's important. The p-value right here, p, 0.0015. So 1, 2, 3, 4. Usually we round p-values to 4. Not always, but that's kind of the standard. Again, pay attention to the instructions on the test. So I go to the fourth place, one to the right, I get 0.0015. So that is my p-value. Well, I compare that to alpha. If p-value is less than alpha, I reject HO. Reject HO. What is the conclusion? There is significant evidence. Sufficient or significant. You could say either one. Sufficient evidence, significant evidence. To support should be a lower key. Support the claim that the mean, what I'm writing here, I'm supporting the claim. The claim is the alternative, so I'm writing in words basically this alternative. The mean waiting time is less than 5 minutes. So your conclusion, I can reject the null in favor of the alternative. What does the alternative say? The mean what? Mean waiting time less than 5 minutes. So that is the hypothesis test for a mean in this particular context. Right, number 12. In tests of a computer component, it's found that the mean time between failures is 520 hours. A modification is made that is supposed to increase the time between failures. Test on a random sample of 10 modified components gave this following data. At the 5% level, alpha 0.05, test the claim that modified components, the mean time between failures is greater than 520. using the p-value method. So my null hypothesis is going to be, well, nothing improved, nothing changed. So null is a status quo kind of hypothesis. Nothing going on here. It's not guilty of getting better. All right, H1. My alternative is that the new time between failures, which would be an improvement, right, is greater than the prior mean, which is 520. Okay. So now I need to do my test statistic, which would be T. In this case, 9 degrees of freedom. And then my p-value, and then we'll make a decision and conclusion. So I'm going to do put this data into a data list. So stat edit, I'm going to put it here in list 1. I'm going to type in this data. I'm going to pause the video, pause the recording, I should say. You can pause the video. I'm going to put in the data and then come back. Okay, so I have the data entered here in the list. And what I can do, I don't have to do this. It just depends on how you choose to use the function t-test. Now I'm going to do stat calc 1var stats, and then make sure that frequency list is blank. I'm doing it for list 1 and hit enter. So this computed x bar and s and n, which I need to do the t-test in the calculator. So I say stat test number 2 t-test. And if I leave it on stats, notice it copied over, like I mentioned, x bar, s, and n. But I still have to input something, because I have to input my null, which is 520. And then I have to input my alternative, so don't forget to do this, which would be greater than in this case. And so I could calculate it this way. However, you don't have to do that step when you run var stats. It's up to you. Some people like to just leave their tests always on stats, but you could also just come over to test. You just put the data in list 1. I do t-test and I choose data. And when I choose data, I still put in my mu0, which is 520. And then I choose my list. I tell it what list my data is in, second 1 for L1. It was already there, but if it wasn't, that's how you do that. Put the frequency at 1, choose your alternative, and then hit calculate. And so my test statistic here is 2.612. My p-value is 0.014, pardon me, 0.0141. I round to 4 decimals. So comparing my p-value, 0.0141 to 0.05, p-value is less than alpha. So our decision is to reject the null hypothesis. So reject HO. And what does that mean? There is sufficient evidence to support the claim what claim? That the mean, what does mu represent? Population mean, time between failures, right? So I'm just really, I'm supporting what? This, I'm writing that in words, is greater than 520 hours. So now the modification did improve the failure time between failures, the time between failures. That's what we can infer from this data. All right, number 13. A manufacturer considers his production process to be out of control if defects exceed 3%. A random sample of 85 items, 5 are defective. At the 1% level, 0.01 alpha, this is alpha, level of significance, test if the defect rate is greater than 3%. So in this case, I'm not looking at a mean. I'm talking about a proportion. And in the sample proportion, this is x. And in the sample proportion, this is n. And this is what it has been in the past. He wants to test if the defect rate's greater than 3%. So my null hypothesis and my alternative, he's trying to test, and sometimes alternative is called the test hypothesis, is P, the proportion, greater than 3%? Do I have evidence in this data that the actual population proportion is greater than 3%? Well, and then here, the population, then you do an equality for the null, which is 0.03. So I want to find my test statistic. Well, in this case, we're going to run one prop z test. So I'm going to get a z as my test statistic, and then I'm going to calculate p-value. So I run my stat, and I go to tests. Number 5, one proportion z-test. One proportion z-test. What's my proportion under the null hypothesis? 0.03. Enter it as a decimal. What's x? Well, it's 5. 5 were defective in the sample. How big was the sample? N? 85. What does my alternative look like? Greater than. So that's already on. Greater than. Then I hit calculate. And so this will give me z, which is 1.558. And p-value 0.0596. Well, that p-value is greater than 0.01, so we do not reject. You could say do not reject. Sometimes it's fail to reject, or do not reject. Either one. Fail to reject HO. What does that mean? There is not sufficient evidence So some wording similar to this. There is not sufficient evidence to suggest this right here, which is the defect rate. That's the proportion of defects, right? So the defect rate is greater than 0.03, which is 3%, the way it's worded in the original problem. Using the context of the problem here, greater than 3%. Okay, so that is your conclusion for this problem. That also concludes the review exercises that will help you prepare for the test. It's not meant to be a perfect one-to-one correspondence, so also please remember to study your notes and your homework.